Okay, so so let's start, Joseph.
Yes.
Okay.
I can start now.
Okay, I will give a you.
Say something in Chinese to introduce me, and then I will start. Not too long, okay? To save time.
OK， 好，那大家好。那刚才呢，其实我本来想用英语介绍的，那因为那个 Joseph 呢说，让我直接用中文介绍。那这样子的话 ，So Joseph, I will introduce you in Chinese, OK?
Yes, of course, yes.
Yeah. 那 Joseph 呢是这次活动呢是我们这个 AI Time Master， 我们叫 AI Time 大师的一个讲座，这也是我们那个深圳国际国际信息中心呢第一次的这种 AI Time Master 的一个活动。那这次我们非常有幸呢请到了这个图灵奖获得者 Joseph Sifakis。那当然这个图灵奖获得者呢，这个 Joseph 呢也是这个法国科学院的院士。而且呢，他其实有名的呢，就是当年呢，他创立了这个法国的一个非常有名的一个研究中心，叫 veracity 的这个研究室。这个研究就有点像国家实验室。这个国家实验室呢，其实是专注在这种比如说这个模型 checking 啊，还有这种相关的一些技术。这个从中国的咱们国内来讲呢，有点像软件工程，就是模型 checking 呢，就相当于模型化的软件工程啊等等相关的一些研究。那最近呢，这个 Joseph 呢，他其实在做更多的呢，就是人工智能啊，怎么来做自动驾驶啊，就是工程化自动驾驶啊这些相关的研究。在之前呢，他是因为在软件工程方面的一些著名贡献呢，获得了这个图灵奖。后来呢，他就开始到这个 AI， 到这个相关的一些自动驾驶系统相关的一些研究里面。他之前其实也在法国的 École 的那个 Polytech， 那是一个法国非常有名的理工学院，有点相当于在法国的理工类最好的大学吧，在里面等等相关的一些。那当然，Joseph 呢其实跟清华也有很多渊源，他也是我们清华那个计算机学科顾问委员会的成员。那下面呢，我这里就不详细多介绍了，我只是稍微提一下。这次呢也是非常偶然的机会，正好 Joseph 前段时间给我发信呢，提到他最近出了一本新书。那我说，哎，趁此机会呢，是不是应该给我们中国的这个年轻学者啊，还有这些同学们呢，包括业界的朋友介绍一下这本新书？而且这本书呢，其实也是一个非常有意思的一本书，就是把人工智能呢，包括知识啊，包括智能方面进行了一些阐述。那所以我们就邀请了 Joseph 呢，欣然答应。那我们正好有这么一次机会。那今天在这个 talk 完了之后呢，我们也请了几位清华的教授呢，跟 Joseph 一起来做访谈，相当于我们探讨一下人工智能的一些未来。好，今天大概就是这么一个情况。Okay, Joseph. So I just quickly introduce you.
Okay, thank you very much for the introduction. Thank you. Okay, I can start. So. Professor Jie Tang, thank you for inviting me to give this talk to present my recent book, Understanding the World, published by Springer. Of course, the book discusses a lot of topics, and today I have chosen to take a very important one, that it is about to compare machine intelligence with human intelligence. And to start, I will say that there is currently a lot of confusion about what intelligence is. And this is also fueled by the media and the large technology companies that spread opinions that suggest that human-level AI is only a matter of years away. And of course, there is also this mythology about machines being super intelligent, and some believe that machine learning will enable us to meet the intelligence challenge, and this is only a matter of time. Of course, I don't agree with all this, and in order to see what intelligence is, it's enough to open a dictionary, and you will see that intelligence is the ability to learn and understand and think about the world and do something very well. So machines, of course, exceed the human intelligence in being able to compute faster and more accurately by solving problems that are algorithmically hard, but machines cannot surpass humans in understanding the world and adaptation to changes on their environment, and this is something I'm going to explain in this talk. Now, today there is still a big gap between machine intelligence and human intelligence. This is something I'm going to explain, we talk about weak AI, weak artificial intelligence that gives only the building blocks for building intelligent systems. And I believe that a big step toward a strong AI will be to develop autonomous systems that are capable of replacing human agents working in complex organizations. So in my talk, we'll talk mainly about autonomous systems that are distributed systems that involve many agents. Each agent pursues specific goals and coordinates so that their collective behavior satisfies given global properties. And of course, just to give you an example of such autonomous systems, if I tell you that self-driving cars are such autonomous systems where each car has its own goals, but globally we would like the system to be safe and also not to have traffic problems. So autonomous systems are essential for achieving the IoT vision. They emerge from the needs to automate existing organizations, as I said, and autonomous systems are critical, are not intelligent systems that play games only, but they replace humans, so they have to manage dynamically changing sets of conflicting goals to cope with uncertainty of environments, to harmoniously collaborate with human agents. And I will explain also that in addition to achieving intelligent behavior, the implementation of autonomous systems involves very complex systems engineering problems that are often underestimated, and I will explain this. So this is an outline of my talk. First, I will talk about criteria for comparing machine and human intelligence. Then I will talk about autonomous systems and the difference between autonomy and automation. That is very important to understand. And then I will talk about mental systems that are a kind of extension of autonomous systems. So this is something I discuss in my book, where I try to see how I can extend my model of autonomous systems to reach to some extent human intelligence. And then I will discuss some issues regarding the future, the impact of intelligent systems. Okay, so this is an outline of my talk. And without delay, let me talk about criteria to compare human and machine intelligence. One criterion that was proposed by Turing is the Turing test. So Turing's idea was that we can experimentally distinguish a computer from a human by analyzing their answers to a series of questions. And if we cannot distinguish them, then the computer is as intelligent as the human. So how goes the Turing test? You have a computer A in a room and a human B in another room and an experimenter C that sends the questions and receives answers. So you have here written questions and receives answers. And if C cannot tell which is the computer and which is the human, then A and B are equally equivalent. And probably also you have read in the news some information saying that a machine passed the Turing test. So there are discussions whether the Turing test is an adequate criterion. And my opinion is that it's not an adequate criterion because the success depends on human judgment that is subjective. And also it depends on the choice of the type of question. So I can choose the question so as to favor, for instance, the computer. And also my opinion is that the test cannot be a question-answer game because you cannot account for human intelligence only through this game because humans can speak, can move, have social behavior, and this cannot be captured by this game. So in a recent paper, we propose another test to compare human and machines. We call this the replacement test. And the idea is that a machine is as intelligent as a human if I can, the human performs a task in a system, if I can replace the machine, the human by the machine, and the result is seamless. I mean, there is no change in the overall system behavior. For instance, I will say that a machine is as intelligent as a human driver if I can replace the human driver by the machine. And of course, for that, you have also technical criteria to decide if the machine can replace a human. And of course, if we adopt this criterion, then being intelligent will mean not only computational intelligence, but also if you want to replace a human by a machine to drive a car, you will have to perform all the sensory motor functions and to implement this in machines, and this is a non-trivial problem. Another criticism that has been addressed to Turing test is the following, that is discussed in this Chinese room argument proposed by the American philosopher John Searle. So the experiment here goes as follows. I have a person here that sends questions in Chinese to a person or a computer, B, that has a list, so has a database that contains all the possible questions that you can imagine in Chinese and their respective answers. So when B receives a question, it can go to his database, find the corresponding answer, and handle the answer to C. So B does something that is mechanical without understanding the answers. So this is a thinking experiment that shows that in fact any experimental criterion that is based on question-answer game is not adequate, and you cannot establish a difference between computing and understanding. And I think this is also a good criticism to Turing's test. Now, another way to consider the problem of comparing human and machine intelligence is to consider the different types of knowledge that the human and the machines develop. So let me start with the observation that the human thinking, in fact, combines two systems of thinking. So here I'm using the terminology from this book of Kahneman. It's a very well-known book, Thinking Fast and Slow. So when we think fast thinking is non-conscious, automatic, effortless, and this is the kind of thinking we use when we walk, when we speak, when we play an instrument. So when we walk, for instance, our brain solves a very, very complex computational problem, but we don't understand. It's solved automatically without understanding. And then you have slow thinking that is conscious, controlled, effortful, and this is the kind of thinking we use when we reason, when we solve a mathematical problem, we develop scientific and technical knowledge, but just reasoning about the world. And there is a striking difference between these two systems of thinking and the two models of computation we have today. On the one hand, we have conventional computers that we program, they execute algorithms, and here we have a model-based knowledge. We have a model, and we have procedural reasoning to say how to compute functions, and this, of course, can be analyzed, understood, and verified. And on the other hand, we have neural networks that generate empirical knowledge after training. So this is data-based knowledge, and they don't execute any algorithm here. They can distinguish, say, between cats and dogs exactly as children can do, and this cannot be verified, and that's a big difference. So on the one hand, here we understand what we are doing, and here we are just using data to train the network, and then the network works somehow in some manner, but we don't understand how. And here it's important to understand so that there are different types of knowledge, and here I give a classification. So you have knowledge that is non-empirical knowledge, that is a knowledge that we produce through reasoning. So this is typically mathematical knowledge, all the theories of computing, logic, and knowledge when we apply when we reason. And then you have empirical knowledge, all this knowledge. Most of the knowledge we use is empirical knowledge. So we develop through getting sensory information about the world. So simple knowledge like events and conditions, but also knowledge of system one, for instance, what I call here empirical, common empirical or implicit empirical knowledge, but also all the knowledge produced by machine learning and data analytics is of this kind. And then you have scientific and technical knowledge that is empirical knowledge, but for scientific knowledge, you use models to explain what happens. And this is the big difference. So here you can make some prediction without understanding how it works for this type of knowledge. And here only you understand what happens. And this is the real value of scientific and technical knowledge is that you understand what you are doing, and of course you can have prediction. Now, just to finish with this comparison between scientific and machine learning generated knowledge, let's make a comparison. So here I'm having an experiment in physics. So here you have this guy Galileo doing the famous experiment, applies forces to a mass and observes acceleration. And of course, our Galileo, he understood that there is a proportionality between force and acceleration and say, oh, this is the model that explains this phenomenon. Now, assume that I want to train a neural network to distinguish between cats and dogs. In that case, I will have an experimental phase. An experiment, I will show a human agent images, and the human will separate images of cats and dogs, and this is the results here. So I will label the images, and then I will train my neural network to distinguish hopefully between cats and dogs. The problem is that here I have no explainability. I have no formal model that explains the relation between the image and the outcome of the experiment here, cat or dog. And this is the problem. And this is discussed a lot in AI community. So this is the issue of explainable AI, and I'd like to on this a bit. So I have a neural network here with inputs and an output Z here. And I would like to, for a given neural network, to find a mathematical function f that characterizes the input-output behavior. So first of all, I would like to say that this is possible, at least for what we call feed-forward networks. So for networks that are not recurrent neural networks, no loop. Why? Because if I know the function computed by each node, and the function is a function like this one, you have the weighted sum of inputs, phi. Phi is some activation function here. So if we can always propagate the inputs to compute the output. So theoretically, I can compute this function f for some classes of feed-forward neural networks. This is possible, and then this is a very interesting result because I train my neural network, it solves the problem, and then I can get a mathematical function. So the mathematical function is constraints between inputs and outputs. And then I can use this mathematical model to reason about the properties of the neural network. So these are very interesting results, and I think this allows connected data-based knowledge to model-based knowledge. Now I would like to finish with another remark concerning neural networks. An important question for neural networks is what they are good for. Also, we know many impressive results, but can I use neural networks to solve any kind of problem? And the answer here is no. And let me try to explain this. So here I'm considering a neural network that receives as input black and white bitmaps. So the inputs are arrays or elements of length SAN, zeros and one. Zero, say, for black and one for white. Now, so I have functions that can compute this. And these are Boolean functions, clearly. And of course, I can build a network that separates cats from dogs. But what about a network that will have this behavior? So it will receive a black and white bitmaps and will will give even or odd, depending if the number of one is even or it is odd otherwise. And it's clear that for this kind of network, if I change a bit in the input, the result changes. think about that. I don't want to further discuss this, but perhaps in your comments or the question answer session that will follow, we can discuss this. Now, let me talk about autonomous systems and their comparison with automated systems. So here I'm considering 5 different kinds of systems: a thermostat, an automated shuttle. As you can see here, this is something you see in the airports, and chess robots, football robots, and an autonomous car. And okay, so these systems interact with their environment. So what is important is to understand what happens in their environment. So for the thermostat and the shuttle, the problem is very simple. They receive just numbers about the state of the environment, and decision making also is very simple. So I can define statically the control here and here. The problem changes with a chess robot. Not, of course, the environment is still static, but for the chess robot, I cannot give the control of these robots statically. Because I have an explosion of states, I cannot do that. And of course, the problem becomes worse when we have a football robot, because here we have the environment that changes dynamically, and also all this should be computed dynamically, and it becomes even worse for autonomous cars. So these are automated systems, and these are autonomous systems to some extent. And let me try to give a functional characterization of what does an autonomous agent. So what does an autonomous agent? Here I'm considering the autopilot of a self-driving car. So it's a reactive system. It sends commands to the external environment, and I distinguish between internal environment that the autopilot can control and the external environment with all the external obstacles. I have sensors, I have actuators, I receive sensory information, and what it means now to behave intelligently and in an autonomous manner here. It means that I can understand what happens, I can decide adaptively, and also this self-learning function is very important. I'm going to explain this. So how it works, I receive sensory information, so here for cameras, from sensors of any kind, and this perception function will be probably implemented today using neural networks to distinguish the different obstacles. And then you will need to build a model of the external world, to build a model, a semantic model of the external world. And based on this model, so the model will say, for instance, that around you, you have all these obstacles, okay? And this is the state of all these obstacles. And then based on this model, you will make decisions, and making decisions means that you will manage goals. So for instance, for self-driving cars, you have many different types of goals. You have goals that are long-term goals, short-term goals that are safety goals, for instance, avoiding collision, staying on a trajectory, and long-term goals. I am in Beijing and I am driving to some other place. And then for each goal, you will have to generate plans, action plans. And action plans are sequences of commands that are sent to actuators. In fact, for each goal, a plan is a set of sequences. It's not just a sequence, because you should be adaptive to changing situations here. Now, this is also a very, very important function, self-learning. Why you need self-learning? And here you are using a knowledge repository. So the knowledge repository, you have knowledge that is stored here, pre-registered knowledge. For instance, for self-driving cars, you can say that I know the properties of a truck or of a car I see here. So I see a car that is a Mercedes, and then I know the properties. And this allows better predictability here. But also self-learning is to estimate what happens to learn new situations and new goals. And this is not very much developed in current autonomous systems. Okay, so I hope this is clear. So to build such an agent, I will have some complexity problems. One is complexity of perception, of course, because the environment, for instance, for my car can be ambiguous, can be vague. I can have complexity of uncertainty. This is a very serious limitation factor here. Why? Because my environment can dynamically change in some unexpected manner. I can have critical events, rare events, failures, attacks. I can also have entirely new situations that are not anticipated at design time. And then you have the complexity of decision also, that is, we don't know how to solve this problem today, is that you have different types of goals. For each goal, you have to generate plans, and this involves some computational complexity. But also the problem is that you have different types of goals with different time constants, and this is a problem. I'm not going to say more about that, but we don't know how to build such systems today for self-driving cars. And of course, in addition to autonomic complexity, so if you want to make your system autonomous, smart, intelligent, you have to deal with these issues. But now the problem is that once you have an intelligent system, you have to integrate it in, for instance, for self-driving car, in an electromechanical system. And this involves other types of problems, because what you get finally is a product, and the product should be trustworthy and provide safety guarantees, for instance. So this is the reason I want to talk about the critical systems here, because, as I said, autonomous systems will be critical systems. And we know how to build critical systems of automated critical systems. And we have standards about that, and we have design methodologies about how to do that. What I would like to emphasize here is that these design methodologies are not applicable to autonomous systems. Why? Because they are model-based. So here you make a detailed analysis, and you start from requirements, and you code components, then you integrate components and this is not possible if you have, say, neural nets, because they are not model-based. So if we have applied successfully these methodologies to build, say, flight controllers. So because you are model-based, you can reason about your system and say, oh, the probability that I have a failure is less than 10 to the minus 9 failures per hour of flight for flight controllers, for instance. And in order to be approved by certification authorities, this is what is required. And of course, this you can do that because you are model-based. But of course, today you cannot these methodologies, and industry today, companies like Waymo, NVIDIA, they don't apply these techniques, and they build autopilots for self-driving cars just by using machine learning techniques. So the situation today is the following. On the one hand, you can build components that are very reliable, that are trustworthy. And on the other hand, you can, there are companies, as I said, like Waymo and NVIDIA, that develop end-to-end machine learning enabled systems. So here, for instance, for self-driving cars, you have a huge neural network. It receives frames, and it produces steering angle and acceleration, deceleration signals. So you can, if you have money, you can buy this product. Of course, the problem is how you will integrate it in a car. And here, today you will not. I mean, these solutions will not be accepted, I think. So what I consider an important work direction for the future is to try what I call hybrid design flows. So to try to build intelligent systems, autonomous systems, by integrating. So for instance, for self-driving cars, you will have neural networks to solve some problems like perception, because you cannot solve the perception problem otherwise. And then you will have model-based components, for instance, for decision making. But there are technical problems how to put the two types of systems together. I don't have time to discuss this. Now, let me talk about mental systems and explain why I have introduced this model. So what is a mental system? A mental system is an extension of an autonomous system. And you see here I have almost the same architecture. At least the situation awareness and decision making are the same. And so this is what does our mind. In fact, we have a function to understand what happens and make decisions. And now the environment will have the internal environment. The internal environment is our body, in fact. And the external environment is the world with all the social environment. And we have sensors, of course, our body has sensors, and we have actuators. So the two functions, the two modules, situational awareness and decision making, are almost the same as before. What changes here is this. So what changes for the human mind? What changes is that we have the ability, to build a model of the external world that is very remarkable. And also we have this ability of introspection. Introspection means that we can look at this model mentally and understand what is the situation. And based on the situation, so what allows introspection? Introspection allows to understand what are your needs, and depending on the needs will emerge feelings here. And also the knowledge repository for humans has something that is a value system. A value system has scales of values that we use to evaluate the cost of actions that we perform. So when we decide, on the one hand, we have feelings, and feelings have intensity. And on the other hand, we have this value system to estimate the cost of the actions we want to perform. And this is what we call, we make a comparison, and this is something I'm going to explain right now. So it is believed that not only humans, but organisms make choices among several alternatives based on some value system. And so my mental system will use, on the one hand, this individual value system to associate value balance to actions. So positive value will mean benefit, recognition, satisfaction, and negative value will mean loss of money, punishment, shame, lack of esteem. And then you will have also the intensity of feelings that express needs. So where the individual value system comes from, I don't know, but we have this value system in our mind, and this reflects a common value system that is developed in society. So organizations develop a common value system. Just to give you an example, if you are living in an organized society, you have a collection of value scales. You have economic value scales. So these are monetary values. If you go to buy something, to buy bread, you will pay money. But you have also penal value. So if you do something wrong, then you will go, for instance, to prison for that, or educational values that stimulate excellence, military values, aesthetical values, ethical values. So for each action field, you have this value system, and the individual value system we have reflects the value system of the society. I hope you understand this. And on the other hand, you have feelings that are abstractions of mental states, and you have feelings that reflect needs that are biological, for instance, thirst, hunger, etc. Or you have needs for safety, and if you don't feel safe, you feel fear or anxiety or intellectual needs and things like that. And then for me, the feelings will be represented by state variables of the mental system. So the mental system is, roughly speaking, a machine, that has three types of variables. External variables that represents the state of the external environment, the physical environment, the economic, the social environment. Internal variables that characterize the state of my body. So for instance, the temperature, the heart rate, the blood pressure, and the variables that measure the intensity of feelings. Now, how we decide? So what is an action, first of all? An action changes the values of these variables. And I have actions that are controllable by me, and that are actions that are controllable by the external environment, what I call non-controllable actions. So when an action for an action to be executed, some preconditions must be met. For instance, in order to eat, I should have money to buy food, and I should feel hungry. And then the actions have a value balance. So when I eat, for instance, a hamburger, I will decrease the money that is available, and of course, I will not feel hungry anymore. And then, for instance, if somebody changes the temperature of the room, then this can affect my feeling of comfort. So I hope you understand that the actions have a value balance, and an action can modify different value scales, of course. And then I can have conflicts between actions. So what it means that I can have conflicts between two actions. If actions have common preconditions and I choose one, this may cancel the preconditions of the other. For instance, if I have 100 yuan and I want to buy food and I want to go to a movie, and the cost of buying food and going to the movie is more than 100 yuan, if I choose one, it will not be possible to execute the other. So this is the way we choose, in fact, and we choose based on value balance on actions, and this explains the fact that we choose. And in fact, in my model, choosing between actions boils down to solving an optimization problem in a game. I'm not going to give details about that because perhaps this is not this will. Yes, the details will be long to explain. Now, just to finish about mental systems, I will say that humans are far superior to machines in understanding complex situations because, okay, they possess what we call common sense knowledge and common sense reasoning, and this is supported by innate mechanisms that we have and we have developed throughout our lives. And then let me try to explain this. Because of this value system, the way we build the external, the model of the environment, this is done in a more or less automated manner. And what I call common sense knowledge is knowledge that is built by experience. And these are relations that are enriched in our life. So, for instance, if you consider the parent-child relationship, this is enriched by other relationships, relations of age. So, the father is the age of the father is greater than the age of a child. Hierarchical support. So, the father or the parents support the child, etc. And of course, this knowledge that is built automatically in our mind can be understood as a complex semantic network that we use to understand for the perception function, but also to understand the language. And of course, we have and the common sense reasoning combines automatic and slow reasoning, so system 1 and system 2, that collaborate to develop this kind of knowledge. For instance, you consciously learn a code of conduct, so how to be polite, and then, of course, this is acquired by system 1 and becomes common sense knowledge automated. And also what is very important for common sense reasoning is that it allows understanding situations by combining two things: bottom-up reasoning from sensor level to concepts, and top-down reasoning from concepts to perception. And here I would like to show you an example. So probably you have seen this in the news. You have an autopilot that mistakes moon for a yellow traffic light. So this is some in the news. And this has happened for an autopilot, for a neural network, in fact, and this cannot happen for humans. Why? Because if I see something in the sky that is like a yellow traffic light, I will say, but it's impossible that it is in the sky. So the big difference between neural networks and humans is that humans take the sensory information and can reason about that, so it connects it through common sense reasoning and knowledge to pre-established knowledge. And this cannot happen for neural networks. Let me give you another example here. For instance, if I show this problem, even if the human has never seen such a picture before, or if he knows simply what is snow and what is a stop sign. Now, neural networks, in order to understand this kind of picture, must be trained to recognize stop signals in all weather conditions. And that's a very, very big difference between neural nets and neural and human learning. And just to finish with another example, this is a sequence of images from an accident. And if you show the sequence of images to a human, you will say, oh my God, this is an accident, okay, what a pity. And a machine, of course, can analyze each frame here separately, but it's very hard for a machine to understand that this is an accident. And why? Because it has to link the causally all these images, and this is not possible. In order for machines to do that, it should have almost the same capabilities as humans to have a model of the external world and to connect this information to this model. And this is a very, very hard problem. So this means that you connect sensory information to symbolic knowledge that you have in your mind, and you understand that this is an accident without knowing the laws of physics or whatever. And this is a very hard problem to solve. Okay, now let's try to conclude by discussing a bit about the future and the impact of intelligent systems. So something that will determine the future, I believe, is the social acceptance of these systems. Will society accept intelligent systems? To what extent? Because if society says no, probably, it will not be possible to use them. So, and social acceptance depends on the role of institutions you have in each society. So typically, for instance, when you build a system today, so for instance, if you buy a toaster or a toy, you have some certification techniques. It's certified according to standards, and these certifications will guarantee that if you use the toaster properly, it will not kill you, okay? So same thing for buildings, airplanes, cars, etc. And you have some agencies that guarantee the proper operation of systems. So here I'm giving a list of agencies in the US. This is Food and Drug Administration. This is for aircraft. This is for highways, etc. Now, the problem is that for systems, for computing systems and applications, we don't have standards. We don't have standards that guarantee security and safety. We have some exceptions for critical situations in transport and aircraft and nuclear plants. But for AI applications, it's very hard to apply standards, and this is a problem. Now, I should emphasize that in the United States, they accept autonomous systems without certification by an independent body. So they accept what they call self-certification by manufacturers. This means that Mr. Tesla will says that my car is safe enough, but this is not certified up by an independent organization. And this, I think, is a problem for the future. Other ethical issues I would like to discuss here are the following. In the future, we will have the choice between performance and also, control, having humans in the loops. When we use autonomous systems or intelligent systems, we should make sure that they decide based on reliable information in a neutral way and in a safe way. And of course, this cannot be guaranteed by the current state of the art. The other problem that is, in my opinion, the other question that is also very important here is the division of work between human and machine. We know that technological progress imply loss of skills. For instance, when primitive man used the levers, this made muscular power less necessary for survival, or modern men cannot survive in a forest, which was the case for primitive man. So we lose skills, but the question here is that when we have intelligent systems, intelligent machines, of human nature. So I don't think that for the future, computers can surpass the intelligence of humans, but it is possible that humans accept that computers decide for them, even for very critical issues, for convenience, because of laziness of their spirit. And this is, I believe, this is a bad scenario for humanity. Now, let me discuss more technical issues here. I think that for intelligent systems, we will need a new engineering foundation, and this is what I have tried to explain. Because if we use neural networks, system design cannot be entirely model-based. And of course, we cannot guarantee a design time that the system is correct. So you should know that today, when we build a critical system, when we finish the system, it is certified, and you cannot modify a line of code of the computers you have in the system. But today, you know that, for instance, for Tesla cars, they accept regular updates, and this is maybe critical software, and this is against current practice. So we should find some compromise and modify I mean, we need some, perhaps probably some new results. I see for the future two important problems. One problem is how to integrate in a system neural networks and the conventional components that are data-based, and how to do that. This raises the issue of linking symbolic and non-symbolic knowledge, and this is a very hard problem, of course. The other issue is that it will not be possible to apply the validation techniques we have applied to traditional systems. I have worked in the past on verification a lot, and verification means that you have a model and you verify the properties of the system you build. And this is not possible anymore. So we will proceed by simulation and testing. And this is what happens for self-driving cars, in fact. But the question here is, what it is now to empirically guarantee that the system is correct. I can give you examples about that. For instance, some companies say we have simulated our self-driving car for billions of miles, but we don't have theory that will relate the simulated miles to real miles, and we need some theory about that. So just to summarize, there is a systems engineering challenge. We need new foundations. There is currently a big gap between automated and autonomous systems. Of course, in some near future, we can build the autonomous systems if we simplify the problem of perception, for instance. So I know that in China, but also in Europe, there are some interesting experiments with platoons of trucks, the highways, and of course, to reach full autonomy, this will need some time. Then something else I would like to discuss is how the intelligent machines can help us overcome limitations of a human mind in developing knowledge. Probably you know that the human mind is limited by what we call cognitive complexity. So how you can measure the cognitive complexity of our mind. Human mind cannot grasp, cannot understand the relations that have more than, say, 4 or 5 parameters. This is the reason also scientific theories are very simple. They involve only a small number of independent elements and parameters. If you look at theories in physics, this is the case. So often when we study complex phenomena, for instance, economic phenomena, we do a lot of simplifications that prove to be unrealistic. For instance, typically in economy, you model what is measurable, and you cannot model human behavior. But in the future, perhaps using supercomputers and AI, we can build what I call neural oracles. What are neural oracles? These are huge neural networks that you train to understand complex phenomena, for which you don't have a very good theory for the moment. So geophysical phenomena, economic phenomena, social phenomena. So, for instance, just to give you an example, I know that there is currently a project how to predict, to have a neural, to develop a neural oracle to predict earthquakes. So this is a project that is supported by Google, in fact. So here you have a neural net that has millions of parameters, and that you train to predict, to correlate, in fact, and predict earthquakes. And probably you can have such a neural oracle that with very little theory can predict better than theories. And of course, if for these neural oracles you can extract also some models, then you have a kind of theory. Of course, you will have a theory that will allow prediction without understanding. And this is in the future, I think that, of course, the knowledge production and application will be no longer the privilege of humans. So I see 2 possible scenarios here. Either symbiosis, so humans will be driving the process of technology development by using machines, or you can also have some kind of parallel science. That is, machines can develop knowledge that we don't understand, and this is a completely parallel process. Let me finish by discussing something very, very important, that is exploring human consciousness. So if we want to build a really intelligent systems, finally, we should understand the relationship between mind and brain. So you know that this relationship has raised a lot of discussion in scientific communities. There is discussion whether the mind really exists or not. But this is, I mean, I don't care about that, whether the mind really exists or not. What I know is that mental phenomena are very important for understanding human behavior, just as software is very important to understand for understanding what your computer does. So I think that in the future we should try, in fact, to connect mind phenomena with brain computation. And I know that there are a lot of projects that focus on brain today. I don't think that these projects will get anything interesting in explaining mental phenomena. We should make an effort to connect the two. And here I mentioned in a European project that it was on brain and promised to deepen on human consciousness. And of course they failed, and any such project will fail, I think. So in my book, I advocate this idea to study the Big Bang of consciousness. As we study the Big Bang of the universe, to have projects that study how cognition and language appeared through evolution, because, okay, through evolution, humans became more and more intelligent and developed all these faculties. So I think that this is something very challenging, and I hope that in the future the societies will be interested in this problem of the Big Bang of consciousness. And I think I will stop here to leave some time for discussion. And I would like to thank you for your attention and finish with this quote by a famous Swiss psychologist, Jean Piaget, who says that intelligence is what you use when you don't know what to do. Thank you very much for your attention. Thank you very much.
Thank you. Thank you very much for the nice talk. Thank you, Joseph. So, any questions? I guess we have some. So we have some audience actually in this room meeting. So probably they can ask questions directly. And also we have some questions from the different channels of the broadcast. And we will copy that question here. So any question here?
Yeah. Yeah. Can I speak?
Yes, I can hear you.
Yeah. So thank you very much for the excellent talk, Sifakis professor. Yeah, so thank you very much. Yeah, in fact, I once worked in l'Inaria in Paris, France. So you were very famous in that time when I was a postdoc working there.
Thank you.
Yeah. So my question is about the uncertainty problem. So in artificial intelligence research area, we think of the uncertainty problem. It's a very huge challenge in neural network model, because it is intrinsic or inherent problem existing in neural network architecture. Because in this architecture, that's a kind of equivalent solution for the model. So, so my question is, what do you think about how to deal with this intrinsic problem existing in neural network? Thank you very much.
Okay, so the question is how to deal with the uncertainty of the neural network, or to cope with the uncertainty of the problem you deal with. I think that the important question is the following. you have, for instance, if I consider in a self-driving car, you have to train the neural network to cope with many different situations.
Yeah.
If you train them by using only raw data, just data, this is hopeless. I think that you should, when you train the neural network, use a semantic model and structure the data. Let me give you an example here, because I'm working on that. For instance, I want to train a neural network to recognize some situations, not a raw data, but to recognize a roundabout, to recognize an intersection. This means that it should be able to recognize some complex structure as such, and for this also I should teach. I mean, how to what I should know what are the main characteristics of these situations, and also I should put emphasis on my training depending on the importance of the situations I will encounter. Okay, and so training should not be only with data, but with more complex structures that add some semantics and characterize the diversity of situations for which you want to be trained. If I don't know whether I am clear on that. Or for instance, you want to have a network that recognizes dogs. Of course, one solution is to give just pictures of dogs, okay. But another thing is to make something more structured and consider that all these pictures are projections of something, and to have some model and okay. I mean, you should introduce models in learning somehow, okay? Otherwise, if you use just flat data without semantics, I think that you will have always problems.
Yeah. Thank you very much.
But these are very hard problems. I think we should try to connect machine learning to models, okay, in some manner.
Yeah. Yes, thank you very much. Yes. Yeah, we also tried, in my lab, we are working on the problem of the imbalanced distribution in training data. So that's also one aspect of the limitation of uncertainty problem. So another is noisy label problem. Sometimes the label of the samples are mistaken. So that's why we do this kind of research about the imbalanced distribution problem in training data and the mistaken label sample problems. Okay, thank you very much.
Yes, but in fact, just if I can just complement this this answer. I think that the deep problem is how to connect database to model-based. This is the big challenge in AI, in fact. And I think that the example I gave with the autopilot that confuses a yellow light with a moon, okay? If you can contextualize this and say, but the yellow light cannot be in the sky, okay? I mean, it's very simple remark, okay? So you should be able to contextualize data-based information and filter this, okay, to protect against wrong decisions also. Yes.
Yeah. So that's why we should take use of some environment conscious.
Exactly.
Yeah.
And now the problem becomes, I'm working at that, in fact, for self-driving cars. And the problem is how you characterize the environment of a self-driving car. Because today, the autopilots that are developed by Waymo, for instance, and NVIDIA, they rely only on frame analysis, okay, on video frame. And this will not be efficient and effective, I think. Okay, I mean, this is a very, very important discussion, and send me an email. I can send you papers about that, how to model the external environment.
Yeah. So model problem is very, very important.
Yes.
Thank you very much.
Yes. But this is not a simple problem, because you will have to represent maps and things like that, and raise the level of abstraction. Okay, too long. Thank you.
Thank you very much.
Thank you very much. Any other questions? Haitao, you have some questions.
Yes. Dear Professor Joseph, okay, it's very nice to hear your excellent presentation. Can you hear me?
Yes, of course, yes.
Okay. So I would like to ask you recently interesting news. There is a breaking news about a Google AI engineer that almost fall in love with a chatbot, a Google chatbot. Do you hear that news?
Yes. I mean, this is yes.
Yeah,
this
very
interesting
news, and a lot of people think about that. That is it means that in a near future that we will the machine will pass the Turing machine test. How do you think about the machine's intelligence?
Yes, but I have time to explain. Yes. I mean, these are stupid. I mean, this is, of course, people like to hear news like that, of course, because these are sensational news, okay, and all the media propagate. But this is just stupid. I mean, this is completely irrelevant, okay, because so this Google engineer says that, I mean, in order to approach human consciousness, you should have understanding. Okay, if you don't have understanding, that you cannot. Let me give you a test. So this is the killer example. What's the killer example I give as an example of what machines today cannot do? You see, you can have machines that make abstracts of text. So you give the book, and the machine will give a text that is the abstract of the book. You can have machines that give the abstract of a video. You give a video, and the machine will give a video abstract. Now, I would like to have a machine that will take a video and will give a text abstract. Do you think this is possible? By all means, this is not possible. I challenge any machine to do that. And the problem is that as long as you remain in the same representation, so I have text in English, I translate in Chinese, this is okay for the machine, because it's without understanding, does some manipulation. But if I show the machine a video, like the video of the aircraft accident, okay? And I tell the machine not to give a summary of the video, but tell me what happened in Chinese or in English, okay? You change mode of representation. And in order to change mode of representation, the machine should have some pivot model. And this does not exist. At least misunderstanding, in fact, okay?
Okay.
So
Thank you for your answer.
This is, yes, this is nonsense.
Yes. Okay. Yeah, that's very, very interesting. Yes. Thank you.
Great.
Thank you.
Okay. So any other questions? Okay, so probably we can also, Okay,
yes, I can hear you. Yes.
Hi, Professor. I'm AI timer. Yeah, and thanks for your representation about AI, and you really gave us a lot of new perspectives on the next generation of AI. So I have a question about that. As we all know that at present, it seems that the neural symbolic model is stronger than the pure neural model. in terms of reasoning and interpretability. So I want to know that how do you think that combining symbolic information and neural network is the only way to go to have a further study for the cognitive intelligence? So I want to know, how do you think about it? Yeah.
Yes. Okay. That's what exactly I said, because human mind combines concrete information, concrete that comes, so database that comes from sensors of our body. And also we have all this symbolic information. Symbolic information is all the concepts we have, okay? So you have the concept of door, you have the concept of freedom, okay? And then you have relationships between these concepts. And this is abstract information, okay? So if I say a door, this characterizes all the possible doors you can figure out. And this is a concept that emerged, we don't know how. And this is the ability of human brain, but also of the brain of other animals. Other animals also can do that. The problem is that a neural network, you can train it to recognize doors because you tell him this is door, but there is an action, there is an operation of abstraction that the brain of animals and the brain of humans can do, and neural networks cannot do. And think about that, because this is very powerful. So the primitive man, the primitive brain of man, initially he was looking stone, different types of stones, and suddenly he said, oh, all these objects have a common characteristics, and let's call them stone, okay? So this is an operation of abstraction. So in logic, you use quantifiers to do that, and you pass from concrete images of stones into the abstract concept of stone. And this is an ability that has the human mind and has the mind of many animals, but machines do not have this ability, okay? You can train machines to recognize stones, but never machines will say, oh, I look at this universe and I learn, and all these objects, I'll call them stones, okay? This is completely missing from machines. And I don't know how to do that, okay?
Okay.
And this is a big difference between human intelligence, and this is understanding. In fact, understanding means that I can link concrete information to abstract information. Okay.
Yeah. Thank you for your answer. And I'm sorry, another very short question. And I have a assumption. So do you think that whether there is a day, maybe the neural network can take into account perception and cognition without any symbolic information? So do you think whether is a day neural network can take over everything?
No, I mean, neural network is just a device, okay? It takes value, it learns how, what it does, a neural network is some interpolation. So they learn points in a space, and then you interpolate, okay? But even they cannot extrapolate, okay? If you understand the mathematical meaning of these operations, they cannot even extrapolate. So, it's very poor what they are doing. They are doing it very, very well, but it's very poor with respect to what the human mind can do, or even the animal brain can do. Okay.
Okay. Thank you for your answer.
Thank you.
Okay, thank you very much for the questions. So actually, Joseph, we also have a discussion panel after the talk. So probably we can save some time. For the panel. So I want to invite several professors from Tsinghua University. One is Professor Chun Yuan. Chun Yuan is a professor in Tsinghua, and another one is Erica Han. Erica Han. Erica Han actually is also a professor in Tsinghua University in Shenzhen. So she is working on AI-related research. And also, I want to invite Haitao Zheng. Haitao Zheng is also a professor in Tsinghua, Shenzhen. So maybe we can discuss some kind of topics, and later on, if the audience have more questions, of course they have many questions, I will send the questions to you maybe by email, and later on
Send
if
me
you're
by
interested.
email. Yes.
Yes. So Haitao, are you there? So we can, okay. So I have some ideas in mind. So basically I have 3 questions. So I want to ask all the panel members, and if you have some kind of answers, or if you have some interesting idea in mind, you just say something. Okay. So the first question actually is, okay, how to deal with the intrinsic uncertainty limitation of the neural network model? Because for neural network model, basically it acts as a black box. So nobody knows why the result is somehow like this, and how the deep learning model processes the input and the generated output. So, and there is some kind of uncertainty in the neural network model. So I want to ask each of the panel members to say your opinion or your ideas about this. So anyone?
I guess go ahead, Joseph. Let Joseph go ahead, please.
Okay, so what I can say is that, so what you call here uncertainty is that we don't understand what they do. And this, as I said in my talk, this is the issue of explainability of neural networks. So you have a black box that receives inputs, produces outputs, but you don't understand, you cannot reason about that. So as I said, the problem is not hopeless completely. And there are many interesting papers in that direction. So what's the idea? I have a neural network, and I can extract a mathematical model that characterizes the behavior. So because we know the behavior, so for neural networks that are not recurrent, you have no loops. But even if you have loops, this is not impossible. But you can compute a kind of transfer function that will characterize the input-output behavior. Once you get this mathematical function, in fact, it's not a function, it's a set of constraints. I can send you papers. There are many papers, many interesting papers in that direction. So once you have this model, then you can take this model, it's a set of constraints, and you can reason about that. You can make proofs, and you have some understanding, even if you cannot fully understand the formulas, but you can use computers to analyze the formulas and all this. So that's fine. If we have this kind of result, this means that we can connect database to some extent to model-based approaches. You can have verification, and the other issue that is very, very important is the sensitivity issue or the robustness issue. So how much robust? If I change, so you know that some networks are very sensitive to changes of their inputs. So if you have a model, you can make some sensitivity analysis, and there are papers about that. So this is the way to go. Now, this approach also has its limitations. Because you can formalize mathematically an input-output relation where you have quantities. So if I have physical quantities, if I have a network that predicts earthquakes or things like that, okay? But if I have a network that separates cats from dogs, then you don't have a model, what is a cat or what is a dog. So, I mean, there are maybe some limitations to this approach. But this is the way to go anyway. I don't know if other members of the panel want to say something.
That's great. Thank you. Perfect. So, Professor Chunyuan, do you want to say something about this?
Yeah. Yeah, I do agree with Joseph's opinion. Yes. So in fact, yeah, in AI research domain, that there are quite some increasing attention on the uncertainty or some robust issues in artificial neural network architecture. So in fact, we call it untrusted problem or non-explainable AI problem, as Professor Joseph just introduced. So I do agree with your opinion. Yeah, the uncertainty problem or the untrusted problem in neural network comes from a wide open areas and wide open range. For example, the data, the training data are always unknown. For example, if we want to distinguish a dog from a tiger, maybe there is an image which is cat. So we call it the in-domain and out-domain problems, or in-domain and out-domain imbalance. So that's a data unknown problem. Another is, as I just said, the label noise problem. So label noise comes from the label problem. For example, when humans do the label for the image, sometimes they may make mistakes. So that's a problem. Yes. Yeah, another is a kind of model structure problem. Model structure means that sometimes this model is just designed by the researcher, but maybe this model is not satisfied the actual or reality environment. So that's a model structure problem. So I think in the AI research domain, there are many research directions to deal with uncertainty problem. For example, to design a model prevent from the overfitting or underfitting problem for the model. Another is to design the model with the ensemble mechanism. Means that we may take use of several individual models and combine them together to draw a more reasonable conclusion. Another method to deal with the uncertainties to take use of the Bayesian method. Bayesian method is a very good model to deal with uncertainty problem. So another method is to take use of the test time augmentation methods. It is not the it is similar to the training data augmentation method, but it is in the test time. So that's several methods which we are often used in AI or machine learning research domain. So in our lab, for the uncertainty or non-explainable AI problem, we focus on the imbalance distribution problem in training data and the label noise problem for the data unknown situation, and some related work you can reference in NIPS 2021, and some work has been submitted to ECCV 2022 and the transactional multimedia. Okay, thanks. It's too long. Sorry. Thank you.
Yes, but if I can say a few words, I'm not a specialist, so I don't know all these detailed research direction. But I think there are two different things. One is how to extract a model from a neural network. If you have a model from the neural network, then you can make some analysis and analyze, for instance, all these robustness, sensitivity issues, or you can make some proofs. So you can gain a lot by extracting models from neural networks, okay? And I think this is a very, very basic problem, in fact, because if there are problems with uncertainty, you can detect them by analyzing the models you extract. Okay, thank you.
Yeah, thank you.
Thank you very much, Joseph, for the comments. So, Professor Han, do you have anything to?
I'll just very quickly on the previous two professors just mentioned. I do agree with both of them. I'll just add something that, you know, if there's a black box we don't understand, then perhaps another way is to find a better model. For example, in my lab, we are reinventing the digital visual cognition with VPU. We call it Visual Processing Unit. That one, we're leveraging our understanding of the human system while also maintaining the maximum compliance with CMOS technology and all the existing learning algorithms and tools. By doing that, we are already surpassed the existing system in performance with roughly 1/5 of the power consumption, but also receiving the same results. What I'm trying to say is, you know, if that's the nature of neural network, then so be it. If we do want to understand it, maybe there's some other way or some other route we can go. I'll just add something very brief to this one, Professor Tang.
Cool, great, thank you very much for the comment. So, okay, so maybe Joseph, let's go to the second question. So actually, the second question is somehow like this. So with the development of cognitive intelligence, will machine conscious approach or even surpass the human conscious? You know, recently actually there are some kind of AI researchers, they are working on that, like a conscious AI, and the idea is that to develop something so that the machine not just have the cognition, but also have the consciousness. So do you think it's possible for that?
Yes. Okay. No, I think that all this is. I mean, all this is nonsense. I mean, these are issues I discuss in detail in my book. So if you have a chance to download the book and take a look, I think that this is clarified. I mean, what it means what consciousness means. Consciousness means that I have a model of the external world and I can see myself.
Okay.
Make choices. I can see how, for a given state, to satisfy some needs, I can make choices. I can evaluate the impact of my choices, and I can do that. So this means that I can link, as I said, concrete information that comes from concrete sensory information to the mental model of the world I have. And this, I mean, machines cannot have a model of the external world and cannot reason about that. So the gap is huge. I mean, this cannot be achieved by studying the brain. Most of the research currently on human intelligence focus on what happens on the brain. And let me try to explain this, why, because there is just a scale problem. Just because you cannot understand what your computer does if you don't know what the software it executes does. If I give you your computer, the hardware, I have compiled the software, so everything is now just signals, okay? I run a program. I give you all the instruments. You can measure all the signals. Can you ever understand what does the computer? No, by all means. And this is a scale problem. So if we don't connect what happens in our brain, because the brain receives all the sensory information, we have a good, more or less good understanding of how the sensory information is mapped on the brain in terms of signals. Then we should go a step further and connect the concrete information to abstract knowledge. There is a big gap. And not optimistic also about closing this gap, the possibility of closing this gap, because this means that we have a semantic model of the world. Having a semantic model of the world means that we have a semantic model of natural language, in fact, because the natural language implements the semantic model of our mind. And if I judge from the very poor results we have, because you see the natural languages and natural language translation, this was a key issue in AI in very early times, okay? We don't have any result about that, okay? So we don't have a semantic model. But whenever you talk about semantic models of something real, this is a big challenge. And remember, 10, 20 years ago, people was talking about the semantic web. Semantic web. What is given the semantic web? Nothing, okay? Nothing. And because we don't work very seriously, in my opinion, to build semantic models of the world, but this is would be a much longer discussion. So I'm considering as absolute nonsense, okay? And it's a pity that scientific communities do not react against that, okay? Absolute nonsense. What is the claim that machines can approach human intelligence? And something else that is completely neglected. Humans have a social behavior. Human behavior is extremely complex, okay? This is the reason I have these value systems in my model, because your behavior is determined by constraints of the society, okay? I mean, to behave like a human, I mean, human behavior is extremely complex, okay? Even to model and to understand, okay? So.
Yeah, to this, I will just add on what Joseph just mentioned. I completely agree with you. Whenever we talk about consciousness, we should first define what is conscious. So this question is more than a technical problem. And in our human society, whenever we say conscious, we often mean by justice and ethics. But concepts as justice and ethics often change over time. And maybe people are doing unjust things in the name of justice. It's also very profoundly related with human emotions and what you just mentioned, our social goods. So in conclusion to this question, I'll just say there's a long way to go. I do agree with you on this part. On this part. Yeah, Professor.
Okay. Thank you. Thank you very much for
and what is if I can complement my answer, what is very challenging is to build machines that, you see, all the studies about the brain either focus on some particular aspects, and there is no global approach where you try to integrate this and take into account all these considerations. So many scientists consider that the question of values is just an ethical issue. Okay, so if it's an ethical issue, cannot be tackled scientifically. We should get rid of all these misunderstandings and all these ideological, confusion that people have. We should try to build machines that integrate all this. So the value system, the issue of feelings. What is a feeling? Feeling means that it reflects a state of, so you build a model of the external environment, whatever you can, and then a feeling is a function that estimates some needs with respect to the state of the system. So I think that we can try to do something in that direction and show also the complexity and the difficulty of the endeavor. Yeah.
Okay. Perfect. Okay. So, Professor Yuan, do you have anything to comment?
Yeah. Because that just as Professor Joseph said, because that, for example, in the autonomous car, for example, the autonomous car, this car mistook the moon for the yellow signal, and many years ago, there is a very similar situation that autonomous car mistook a white car for the white cloud. So that's a very similar situation, and another one caused a very serious accident. So many years before.
Yes, I know.
So that means that we cannot totally trust the AI, because, for example, for human, we have a very, very special emotion. For example, sometimes we may be very, very angry, but we can control our action. But for the AI or for the robot, we cannot guarantee it prevent his his every action. For example, when the robot is angry or with very bad emotion, maybe it can act a very special action. So that's why I think that's just as Erica said, it's a long way for the AI development. So that's my opinion.
Okay, of course, if robot becomes very angry, cannot control this means that it has been programmed not to control. I mean, or it's very hard to model such a behavior. I mean, if it has been programmed and has not been trained, of course, but that's different. Okay, thank you.
Okay, following this, actually, you know, Joseph, I know that you are against of the conscious AI or some idea about that, and also I see that Erica also against of this. But recently, you know, that there was some kind of news about the Google's AI engineer actually fell in love with Google chatbot. You heard that? There was a news.
Yes. But this is completely stupid. Yes, of course. I mean, and I think also that this guy, I don't know, he has been fired or something. I mean, even Google does not like that people tell such a big nonsense. So, I mean, but you see, that's the problem with media. If you say something that is a big lie or a big nonsense, and people like to hear this, because there are other things that people don't like to hear. For instance, in the Western world, people don't like to hear about the crisis, economic crisis, or people are starving, things like that. Okay, so they don't discuss this, but they can discuss sensational stories. Okay, so about Martians invading the Earth or going to Mars, to Mars planet. Okay, I mean. You know that there are a long list of people that wait to go to travel to Mars, okay? And you know all the difficulties. I mean, this is practically, and people are talking about going to live in Mars, okay? And this, you know that this is practically, I mean, technically, this is sending one person, okay, already is very, very challenging and very risky operation. But people tell stories like that, and you see also just for self-driving cars. Elon Musk was saying in 2016 that in 2 years you will have self-driving cars around the corner, okay? Where are the self-driving cars? But nobody notices that, yes. I mean, it's just stories, okay.
Okay.
So Erica, do you want to,
Exactly. Yeah, exactly. Yeah. So I'll just say, in this one, we're actually trying to somehow equivalent love with Turing test. But, you know, in fact, love and Turing test, they are two fundamentally different things. We may fall in love with a person, he may have logic, you know, he may be smart, he may be humor, but, you know, but with this type, with this, we cannot, they cannot really be tested with like how human or how intelligent a system is. Like what we are doing in Turing test, because computers are basically very good content creators. In the meantime, we also need to distinguish between what is love and also fascination and obsession, these type of things. For example, a person maybe fall in love with a car, but that doesn't mean that a car can pass the Turing test as well. We're not talking about the self-driving cars, of course, but these are the type of things this question is trying to, I guess, confuse with. That's my opinion on this one. Professor Tang.
Okay, great. Thank you very much. So I said actually Professor Haitao Zheng is also here. So actually we are just talking about the news that
yes.
Google.
Yes.
Oh, you heard that? Okay. So do you want to share your comments or your ideas about that?
Yes, I think it's a very interesting phenomenon. So in fact, when the machine intelligence develops so fast, the human being will confuse about who is the machine, who is the real person, little by little. So I think, of course, it doesn't mean the machine or robot has the conscious or they can pass the Turing machine, but it means with the development of the AI, the machine can help people doing more service, such as some kind of psychology or some kind of can help people to confirm their emotion or something like this, more challenging works. And in the near future, I think that, in fact, there is many work that something like psychologist, right? Psychologist recently can only served by the human being, right? But I think in some near future, with the development of the some kind of this kind of the emotional detection or emotional suggestion development or emotional advice, it also can be proposed by the machine. I think this is a very interesting phenomenon that in the near future there may be a new job that can be worked by the robot. I think this is in the positive effect. That's my opinion.
Okay.
Cool. Okay. Can I say something about that?
Yes,
so first of all, I said that the Turing test is not a good test, and I explained why it's a not good test. Because it's just a question-answer game. So it's not the criterion, okay?
Yes,
and of course, you can have bias in the questions, etc. Okay, but if the criterion is that if a human performs a task, then I can remove the human, put the machine, and the machine can perform the task. And as I explained, the machine should not only be intelligent, but there is a systems engineering problem. So being intelligent for a machine means that it can perform the movements as humans, okay, and can sense as humans, okay, and this is a problem because humans have multimodal sensory functions, okay, and machines also should be able to implement, and also should be able to do this safely. And safely means that they don't do something wrong. And of course, the probability that machines do something wrong is probably higher than that machines do something wrong. But humans are more resilient. If I do something wrong, I know how to find a solution and undo that, okay, in many cases. And machines do not have this capability. So building intelligent systems is not a problem to have a huge brain, but the brain should be integrated in an environment and communicate and all this. And this is a very, very different problem because this involves also
Okay. So, yeah. Okay. So, Professor Yuan Chun, do you have anything to share?
Oh, yeah. I do agree with all opinions for the professors. Okay, no problem. Thank you. Yeah, I just said that the most difference between the human and the robot, maybe the human can more think about the consequence of something, but maybe the AI cannot think of more the consequence of the thinking, of the action, or something like this. Okay.
Exactly, because we have all this model. We know what means social organization. We know how justice will punish us if we do something. What are, the economic stakes, how economy works. So we have a complex model of the external world, and we can weigh the consequences of our actions based on that, okay? And this is a very, very complex model of the external world, okay? I mean, it's impossible.
The AI
to build machines with such a model, yes.
Okay, cool. Okay, super. So, anyone else? Probably, we have the 3 questions, and thank you very much for sharing your ideas and your comments about the AI and the future AI, about the concepts and about the AI. Everything about the deep learning algorithms. Probably last, so I want to invite everyone, every panel members, to say one sentence or maybe a few words about your thinking about the future, near future of the AI development. For example, what will happen in next year for AI? So maybe let's start with Joseph.
Oh, I have talked a lot about the future. I think that the challenge is how to build the intelligent systems that we can trust. And this is one challenge. And the other challenge is how to understand the relationship between the brain and the mind, so the mental situations. And I think that these are the 2 huge challenges we will be facing in the future. I don't know what can be a horizon. Okay, I cannot predict anything. These are very hard problems, both of them. So let's work and be modest, okay? And be modest, okay? Because the challenge is huge.
Yeah, thank you very much. Okay, so anyone?
I'll just add another part. So in my opinion, right now we are in the phase of still building AI for humans. But I think in the near future, maybe not next year, but in the near future, there probably will be AI for AIs, which means right now we are building machines for humans, but at some point, probably there will also be machines for machines. So that will be maybe another new era of either AI or artificial intelligence. That's what I'll say.
Okay, cool. For AI, for human, yeah. Professor Yuan Chun, do you want to say something? Maybe one sentence or 2? Yeah.
AI can help human in a broad of size, but maybe it cannot bring us the true happiness. That's all.
Okay.
Good.
Okay. Aitao?
Okay. Recently, there is a new rule about Web 3.0, right? I think many people have a different idea, but I think, in my opinion, in the near future, there should be a smart agent network developed by the AI, because everybody can work in something like metaverse or reality. We always need a smart agent to help us to do more and more work, because we have a limited energy, limited time. or limited resources, right? I think in the near future, the AI could be a very smart agent to help the people to make better life. So I think this is, and the smart agent can be a network, can be grouped as a network to help people to not only to make a better life, but a better work. So I think the Web 3.0, I think, is also a smart agent network also included.
Okay, great, thank you. Yeah, so AI definitely has a promising future, but of course everyone talking about it. We are facing actually many challenges, like how to make AI, like with the cognition and also conscious. But anyway, that is challenging. I know that you are against all the fact that the AI probably will not have the cognition or conscious, but personally, actually, I'm very positive about that. So, but anyway, let's try to.
Don't misunderstand what I say. I'm not against. I mean, I think that currently it's not possible. Perhaps machines could exhibit some kind of consciousness in the future, and I have nothing against that. Because if they exhibit consciousness, this means also that collaboration with human will be much, much better than it can be today. But I am saying that under the current state of the art, this is not at all possible. That's what I'm saying. And I am against people who are speculating on that and are spreading fake news about that. That's it.
Okay, great. Okay, so probably we are going to the end of this panel. So Joseph, so probably I will use Chinese to say a few words about your talk.
Of course, yes.
Oh, great.
I will stay online to hear this.
Okay, thank you very much. 大家好，那非常感谢大家参加今天的这个 AI Master 的这个活动。AI Time Master 的这个活动，那我们今天非常感谢图灵奖获得者 Joseph 给我们的这个非常精彩的报告，以及留下来跟我们各位 panel 的这个成员呢一起讨论了 AI 的未来。那非常感谢大家，然后也希望大家呢能够继续关注 AI Time 还有和国际信息中心的相关的一些活动。那在未来，国际科技信息中心呢还会组织更多的这样的高端的报告会。当然呢。今天的那个报告 ，Joseph will share his slides later on with all the audience。那我们也非常感谢这个 Joseph。那其他如果大家还有问题的话，也可以发信给我们 AI Time 的这个志愿者。那我们把所有的问题呢都收集下来，我们会把这些问题发给 Joseph。那 Joseph 后续呢将通过 email 的方式给大家回答这些问题，好吧？那再次感谢大家。大家如果对我们这些活动如果有什么建议的话，因为我们现在国际科技信息中心呢是在深圳清华研究生院，就是主要是落地在这里。如果大家对我们有建议或者希望加入国际科技信息中心的话，也希望大家联系我们。我们这个郑海涛老师呢，就是在这里也在帮我们做这个相关的联络。那当然大家也可以通过直接跟我们联系，好吧？那到最后呢，再次感谢大家。Thank you, Joseph. Thank you very much.
Thank you. Okay. Thank you. Very interesting discussion.
Thank you, Professor Joseph. Thank you, Professor Tan. Bye.
Bye.